for you. Okay, so ladies and gentlemen, let's transition to this new type of modeling. This type of modeling will share certain commonalities with what we've been leading. It will share the fact that we are simulating systems over time when we're simulating their state as it evolves over time. We will be characterizing a situation in the external world according to, okay, I don't want that. I want to get to agent-based modeling here. Here we go. We'll be characterizing the evolution of the system in terms of implicit, characterizing the terms by which it evolves, given the current system state. What are the rates of change by which it's evolving? And that will dictate implicitly how that state evolves over time. And we will use these models in many similar ways to how we use system dynamics models. But the models here will be very different in character. They're almost the flip side of the system dynamics models that we've been looking at. They're not built out of stocks and flows, but a much larger vocabulary. And here, in stocks and flows, we characterize the population as divided up into different compartments, which we called stocks or state variables, according to their characteristics, their current infection status, susceptible, infected, recovered, for example. With agent-based, and for each stock, we maintain data on the number of people in that stock. With agent-based models, we're going to be organizing the model radically differently. We're not going to divide people up into buckets according to their state or characteristics. We're going to instead organize the model according to individuals, and each individual is going to maintain information about its properties, its characteristics, its state. So here, the organization is the flip, as it were, of the system dynamics model. Here, we're going to have one or more populations, each composed of individual agents, and each associated with a set of components. Parameters, which are going to describe sort of fixed assumptions about the model. These could be discrete, countable, things like gender, ethnicity, the product category, or what have you, or continuous, price, birth weight, income. Moreover, agents will each be associated with some state, the current situation as it is right now in time. Some actions that change that state, and some rules that govern those actions firing to change the state. For example, rules governing the transition from one state to another. And then they're going to have some means of interaction with other agents or the broader environment. So they may be a network, so they may be in a spatial context. There's going to be a time horizon and time characteristics. And most of the time, we're going to use continuous time. Sometimes we'll use discrete time. And more than that, there's going to be some initial state, much like there was in stock and flow modeling. So in stock and flow modeling, here we had a situation where we are subdivided according to state. And if we wanted to have a model where we had susceptible males, susceptible exposed males, infected males, recovered males, we would need to separate those states from susceptible females, exposed females, infected females, recovered females to capture the dynamics of each of those. So here we're subdividing people according to their characteristics, their state, and their other attributes. And each stock counts the number of people within that group. If we have stocks for different sort of levels of a system, sort of for a neighborhood and then for a city, it's simply a combination of the others. Now, for agent-based modeling, we have something rather different. We have the model divided up into people, and each such people will be characterized according to properties and state charts or states and their transitions. In other words, characterized according to actions, states, and rules for evolving them. And we will have each unit maintaining its own attributes. So Here, the subdivision is different. We subdivide here over in system dynamics according to state and characteristics. Over in agent-based model, we subdivide according to the individual people. And each unit maintains its own state, whereas in system dynamics, each unit, each stock maintained the count of people. And here in agent-based modeling, we're going to have nested relations, say, between an individual and their family and their neighborhood and their school and their city, which is naturally nested in a way similar to the world, rather than being sort of within the same model at the same level. So here we're going to have a model population, and members of that population are going to be associated with parameters that specify fixed assumptions about those individuals. And a particular agent is going to have a fixed value for those parameters, right? They're going to be associated with states, and those states might evolve over time. And a given person might be associated with multiple state concerns. So in other words, each state chart here is going to describe a particular concern. We're going to have, as in software, a separation of concerns. There's going to be sort of an orthogonal decomposition here between infection-related concerns, and some will be in a state with respect to those on the one hand, versus others having to do with whether or not they seek care from a healthcare center, such as a hospital. There's going to be means of interaction between these agents, and there's going to be spatial context as well. This will give rise to emergent patterns over networks and over spatial aspects that we couldn't neatly describe with system dynamics models. Could we have some sort of state with system dynamics models? Yeah, we could divide up a state, like the ceiling is divided into grid pattern. We could divide up a given area by subscripting the stocks by, I and J, where I is the row and J is the column. It would be fairly cumbersome to do that, but we can do it. Here, for agent-based models, we can describe space in continuous terms, and we can have geographic spatial environments as well. We saw this the very first day when we saw patterns over space, and we'll see emergent patterns as they exist over networks, which capture topology, connectivity between individuals, okay? And these aspects of network context will affect an individual's evolution. System dynamics, thus far, it's not baked into the discipline. There are stochastic system dynamics models. In other words, system dynamics models which exhibit randomness over time. But for the most part, system dynamics models are traditionally deterministic. They, given the current state, the rates of change are fixed, are defined by the current state. In other words, they're given the current state, you could specify the rate of change exactly, which determines the state that obtains in future time points. By contrast, agent-based models are going to be stochastic. There's going to be a lot of stochastics at an individual level. And so to ensure that our results from the model are not simply flukes, we're going to run the model many, many times over. And the good news is, so the bad news is this requires a lot of work. The good news, it can be parallelized efficiently. And these stochastics will actually lend insight. They're not merely nuisances, they'll actually add considerable insight. So a single run of the model might lead to, for example, a particular outcome over time. If we look at the outcome at the final time, there'll be some number of individuals who have gotten sick who are in the rich group or the poor group, and the number of individuals over time who are sick could be plotted out. But if we run the model many, many times, we'll start to see variation between these things because there's some stochastics. In some model runs, the number of individuals who are poor and get infected is larger, and in some cases it's smaller. It's down in this range. Some cases it's larger, and in some cases it's virtually none at all. By contrast, richer individuals, if we run the model, sometimes will have more, sometimes have fewer. But the point is, by running the model many times, we get a sense of variability. There's certain regularities, but there's certain differences. So this is agent-based modeling. Agent-based modeling will occupy us for most of the remainder of the course. And reflecting with that, I'd like to talk about the modeling vocabulary that we will be using for agent-based modeling. Okay, agent-based modeling has a vocabulary that's very different from system dynamics, and system dynamics is characterized by what I would call hedgehog knowledge. It knows just a few things really, really well. It has stocks, flows, and then a few derivative things, you know, well, it has constants, but a few derivative things like dynamic variables that are really not essential, but are conveniences. The power here lies in the combination of the elements. We build up first order delays, nth order delays. We build up elements with target following. We build up elements with aging chains. We build up elements with nonlinear components. So the power lies in the combination of these elements. And analysis is conducted by looking at the values of stocks and flows. Agent-based modeling is, for a lot of computer scientists, more familiar territory. It's interesting. Engineers, people with engineering education, tend to understand system dynamics fairly well based on aspects of engineering education. Those who have come in computer science, not through engineering route, tend to be somewhat more comfortable early on with agent-based modeling. We have a larger modeling vocabulary. We have different subsets of the vocabulary used for different models. And the power here is in the ability to mix and match different characteristics. And we have a variety of foci in our analysis, including spatial components. So what are these components of an agent-based model that we're talking about? What's this vocabulary? Well, compared to stocks and flows, I put a lot of them on the board here, okay? Parameters, these things that specify assumptions and communicate those assumptions from the point of creation to the thing being described. We actually saw those a little bit in our model thus far in the context of system dynamics modeling. They're not exclusive to AVMs. Events describe things that happen on a certain schedule. It characterizes a schedule of events, sometimes just a single one, but generally a series of events over time. We'll have multiple mechanisms for describing dynamics within agents. State diagrams, state charts are what we'll use the most. They look like UML state charts. Do they still teach that in 270 UML? Yeah, and you have state charts that you use to characterize possible states the system could be in. Less, you have probably class diagrams, sequence diagrams. Yeah, okay. Yeah, so state charts come out of UML. They characterize simultaneously. This is important, actually. This is true for these and stocks and flows. They simultaneously describe the states, the actions that change those states, the rules under which those actions take place. Those are characterized by both state diagrams and separately by stocks and flows. Stocks and flows here will characterize, ladies and gentlemen, continuous dynamics. Dynamics involve continuous quantities, particularly quantities which exhibit feedback in their evolution over time. Positive feedbacks, negative feedbacks. It ain't going away. We'll see it within agents in what are called hybrid models. State charts, by contrast, characterize changes between categorical states, sort of I'm susceptible or I'm infectious or I'm recovered. If I want to characterize how much I have in terms of viral load in my body, I'll use the stock and flow. If I want to characterize that I am infectious, I'll use the state chart. Okay. By and large, stocks and flows used for continuous quantities, particularly where there's feedback. So they're exquisite for that. State charts are used for transitions, particularly triggered by outside and triggered by certain rates determined by model state going between certain categorical states. Interagent communication will be a key thing within our models. Ladies and gentlemen, did people here, how many people here have seen ACA in a course? Have you seen ACA in 340 Ring a bell? Yeah, a couple people. So there you may have been introduced to message passing. So situations where you pass messages from one actor to another. We'll see that here. So agents within these models will send messages to each other. That's the predominant way in which they'll communicate, is sending messages to indicate you're infected, or you've been influenced by me, or what have you. There'll be multiple types of transitions for state charts. There'll be connections and networks over which these messages flow. There'll be spatial embedding and mobility and movement of these agents around within space. And there'll be aspects of subtyping involved as well, with subclassing of agents that we might see in later parts of this course. Stochastics will play a larger role in our considerations, particularly for processes we'll be discussing later in the course, calibration and sensitivity analysis. And we'll be talking some about sort of synchronous communication versus asynchronous in the context of messaging, potentially in diverse types of agents. So this is where we're going. I'd like to build together an initial model, okay? I'd like to build together a model that will unite system dynamics and agent-based models within the same framework, but where you can see both in full flight, okay? Time is short, so this model will be, of necessity, very simple. But ladies and gentlemen, start your engines and call up AnyLogic, okay? We're going to, with AnyLogic, build a model that will characterize the same basic system using state charts on the one hand and agents, and also with stocks and flows in the same model. This will be an illustration, in fact, of what we call a hybrid model, a model that incorporates more than one type, more than one paradigm of modeling. And this is a very powerful feature of the software platform we're using, AnyLogic, perhaps its foremost claim to fame. So we're going to characterize a simple system associated with a familiar territory when it comes to system dynamics modeling, namely first-order delays. Okay, we're going to build the first-order delay system. Soon enough, we'll be building more complex nonlinear systems, but time is short, and we need to make time. So, ladies and gentlemen, I'm going to close the AnyLogic screen here. I'm going to close all models, and I'm going to create a new model, and this will be called initial ABM. Compared with SD, okay? And I'm going to set the model time units to be years, okay? So initial ABM compared to the SD, and I set the time unit to be years. Please finish it. Pay attention to the time unit. It carries, it's a choice that carries gravity in terms of model performance. Okay, so ladies and gentlemen, the first thing we're going to add will be old hat. Okay, I'm going to go to a system dynamics area. I'm going to go drag a stock in. These will be unafflicted people. These will be people unafflicted by some condition, and these will be afflicted people. Okay, and I'm going to drag a connection between some, which will be called affliction, okay? I'm abstracting away from what malady I'm characterizing. And I'm going to drag in a parameter that will be called affliction hazard, okay? That will be the chance per unit time I'm going to grow afflicted, okay? And the value of this is going to be 0.015. Okay. And we are going to put in a link between affliction hazard and affliction. And if this is a first order delay, on what else does affliction need to depend? Yeah, on unafflicted. There ain't nobody going to get afflicted if there's nobody unafflicted. So affliction here is going to be, what's the formula going to be? If this is a hazard rate, if this affliction hazard is a chance per unit time of becoming afflicted, what's the formula here going to be? Yeah, unafflicted times affliction hazard, right? Okay, affliction hazard, good. And now let's make sure that afflicted starts with initial value 0 and unafflicted starts with initial value 1,000. Okay? And again, affliction hazard, for those who didn't catch it before, should be 0.05. So if we run this model, what should we see? What will we see here? What would the value of this unafflicted stock be? Anyone? How will that change? The value of the unafflicted stock. Well, here, let's go, to clarify that, let's go drag in. We're going to go to the analysis palette, go drag in a time plot, and we're going to, in this time plot, we will call it states. We will put in data, and the data will be unafflicted SD, and the value will be unafflicted. Okay? So I've just told this plot to plot out the number of individuals in this stock. So let's run this model. What should I see in this graph? It will decrease like a what? Like a, will it decrease linearly? No, it'll decrease like a what? Negative exponential, ladies and gentlemen. Okay, let's set the simulation to finish at time, so stop at time 100. So how did I do that? I went to simulation. So this is the scenario, the experiment. I went over to properties, and I set down in the model time area, I set it to stop at specified time, and I left it at model time 100. So if I run this, I will see a classic first order delay, a draining of that stock. Fair enough. All of this should be familiar to you. There we go. Okay. Now, ladies and gentlemen, the plot thickens. We're going to go in quick order. Okay? So pay close attention to this. First thing we're going to do, now begins the agent-based modeling onslaught. So right-click on this, do new agent type, and say person with a capital P. Capital P person. Okay? Next. How did I do that? I went here, I went new, and I chose agent type. We are traveling, ladies and gentlemen, to parts unknown for most of you. Next, I'm going to go down to the palette, and to give these people an appearance, I'm going to go down to the palette called Pictures, and I'm going to pick a picture from here. I'm going to pick a person, but I know some jokesters in the audience will be picking other things. Okay, I know the forklift or the fighter jet may seem tempted to some. Okay, and I'll leave that to your discretion. Okay, so person, ladies and gentlemen, what we're going to do is we're going to go up to main again. So notice I added that person in, and I added it from this pictures palette. And I added it to their origin. That will be important because I added to the origin. Their logical location will be the same as their visual location. In other words, if we had made it to the right of the origin, their appearance would be to the right of their logical location. Generally, we want to overlap those. Okay. Next, we're going to go to projects menu and we're going to drag in person to main, okay? And dragging that in, you can rename it to be population. I actually did not do that in time, so I'm going to say population. Now, this is not yet a population. Its name belies the fact that one more thing still has to happen. To wit, this thing we dragged in. We dragged from person class into main. We created this so-called embedded object. But we need to change this to be up here, a population of agents, okay? Population of agents here, boom. And we will make it, ladies and gentlemen, 1,000 agents, okay? Despite my impulses, we're not creating a parameter for this because we also hard-coded the initial value associated with the with that stock. 1,000 agents here to match the 1,000 agents that are in this system dynamics model. Okay. Okay, ladies and gentlemen, there's our population. And we're going to say here for the initial location, we're going to say that we're going to place them in the specified point, and we're going to say draw from a uniform distribution between 0 and 500. How did I do that? It's under initial location. We'll say in the specified point, and we'll say between 0 and 500, 0 and 500. Okay? Where did I do that? I did it here. Ladies and gentlemen, in the characteristics of this population, I scrolled down, make sure it's population of agents, size 1,000, and I went down to initial location, and I set this to be X to be drawn from, the value of X. As it's determining, there's a new person that's being created. Where does it live? It lives at, it draws its X value of its location from 0 to 500, and same for Y, okay? It's gonna draw it from that. Let's run this model and we'll see what happens, okay? Here we go. Run the model and we will take a look at what's going on. So there's my population of agents. But right now, are those agents following the behavior of this stock and flow? No. Ladies and gentlemen, these agents need to be associated with dynamics. So let's go add that, okay? So I'd like you to go to the palette. I'd like you to go to the state chart part of the palette, okay? The state chart part is this area. It looks, there's sort of a little yellow state there. And I'd like you to drag in the state chart entry point, and this will be called affliction state chart, okay? And I am going to drag down the state. It will be called, we'll call it here, afflicted within a person, okay? We will drag down another state. We will call it, oh, sorry. I screwed them up, didn't I? This should have been called what? Unafflicted. They start unafflicted. So where did I drag this from? State chart entry point, not initial state point, or state chart entry point. I dragged in a state called afflicted. I then dragged in another state called, sorry, unafflicted, and then I dragged in another state called afflicted. And I'm going to drag in a transition betwixt them called affliction. Now, this transition will be triggered by a rate transition. That means, ladies and gentlemen, a hazard rate. And the hazard rate will be given by main dot, guess what? Affliction hazard. So with the affliction hazard as it lives in main. You'll notice this agent has a reference to their main class in which their population is embedded. So here, this transition will be fired at a hazard rate, probability per unit time given by that affliction hazard. Same basic mathematics in terms of the probabilities involved as we saw in the system dynamics model. Okay? Are we okay with that? Who needs more time? Who needs me to show something that I did? Because I know we're going pretty fast. Anyone need me to show anything? No? Okay. So we're most of the way done here. We just have to do one or two more things. Ladies and gentlemen, I'd like you to go to population. Back in Maine. We're going down Maine, ladies and gentlemen. Going to Maine. I'd like you to go to population, and I'd like you to go to the statistics area of population. I'd like you to, in statistics, put in count afflicted ABM. Well, just say count afflicted because it's in the population, so it's by implication in the ABM. This is going to be a statistic that will count the number of people that are afflicted. And the condition here, it's going to go through each person in the population, call them item. Okay? And we're going to ask item, this is going to be the person, are they in the state person.afflicted? It's afflicted with respect to person, not the afflicted in the state of the stock here. It's the afflicted within person. Okay? So what did I do? I went to population, ladies and gentlemen. I went to the population, I went to statistics, I created something, its name is count afflicted. I made it type count, which it was by default, and I put in the condition item, that's the name of the person. So it's going through each person in the population, calling them item and asking, are you in the state person.afflicted? That is afflicted with respect to the person class, not afflicted with respect to the main class. Okay? Are we okay with that? Are we okay with that? Okay, ladies and gentlemen, next, who needs more time? Who needs me to answer a question about this? Okay, let's go to the graph, and in the crowning jewel of the afternoon, at least by my standards, you can do plus, and you're going to say unafflicted. Ooh, oh my gosh. I'm going to say afflicted ABM, and I'm going to put in the value population dot count afflicted. If I had presence of mind, I would have made it unafflicted because I had forgotten we were presenting the number of unafflicted. I'm going to add one more to do the afflicted SD. Okay, this will be afflicted SD because we already have unafflicted SD. We're going to do afflicted SD. And what is this one going to be? Just afflicted. If you wanted to be careful about it, you could say this dot afflicted. Right? Okay, run. What do you think we'll see? Who needs more time? What did I do here? Ladies and gentlemen, let's rehearse it quickly. I went to person. I added in the state chart called infliction state chart. I added an unafflicted, an afflicted state. I created transition, marked it as a rate transition given by hazard, in other words, and I indicated that this was the hazard rate by which one goes from here to here. It's a probabilistic process. I then went to main. I went to population. I went down to the statistics area. I added a thing called count afflicted. Okay, and then I went to this graph and I added a few things. I added afflicted ABM where I did count afflicted. I added afflicted SD where I did afflicted there in the SD. Okay, so let's run this model. And what shall we see, do you think? What do you think we'd expect to see on this? Anyone? Does anyone see the afflicted ABM here? Where is it? Anyone see it? Look closely. I'll see if I can get a zoom in here. Let's just see view. Does anyone see it? Wherein lies it? Where to 4 is it? Do you see it? It's right here. What is it paralleling? So that's the count of afflicted people. What is it mirroring? Actually, quite closely. What curve is it following fairly closely? The afflicted stock, please. Here we have two systems where the system dynamics aggregate characterization is a pretty good description of what's going on at the agent level. Each agent is subject to a fixed hazard rate, and that hazard rate dictates their chance of going to an afflicted stock. And the system dynamic model counts the number of people who are afflicted and unafflicted. The agent-based model has many, many people, and in fact, you could go browse them here for each person to see what state they're in within the agent-based model. But the point is that the system dynamics model here, it has a pretty good approximation to the dynamics of the individual-based model. Both are characterizing mathematically the same underlying system, just with different levels of abstraction. The higher level of abstraction here is fit for purpose. It's suitable for the task. It's fairly accurate. But soon, ladies and gentlemen, we will be looking at situations with great history dependence of agents, looking at situations with networks, looking at situations with spatial effects, looking at situations where you have individual decision-making by agents based on who's around them in their local area of space. And our ability to characterize that using aggregate models is poor, to say the least. So that's where we're going. This gives you a common point of reference. Almost a grossly simplified Rosetta Stone, where you can look and see the same basic system implemented in two different paradigms. Okay? And if you'd like a little challenge, you could try adding a statistic to the model to count the number of unafflicted people and graph that as well and see how that tracks it. But soon enough, we'll be in situations where the agent-based model and the system dynamics model will have some very significant differences, even in approximating the same underlying situation, because of stochastics, greater level of fine-grained granularity, etc. Ladies and gentlemen, the class is over. Thank you very much for your attention, and I will post this video, which I understand is getting good audio. Thank you.
Hi. See the the population.
Sure.
Equation.
Sure. Oh, I'm sorry. Yeah, I'll try to put it up. This guy here.
Okay, I just had in-state without capital S. So
Yeah, it's capital S here. Yeah, autocomplete is control space. Yeah, it's Eclipse behind the scenes, so.
Okay.
So you should be able to use that. Yeah.
Okay. Thanks.
A question, because you had inquired, I think it was you, about the assignment return. Was it you who had asked? Okay, because TI had indicated he was trying to get them back yesterday or today. Did you get yours back yet? No.
I haven't got mine.
Okay. I spoke to him about it, and he said, yeah, I'd get it done by yesterday if possible, otherwise by today. But I'll talk to him shortly. Yeah.
I have a question.
Yeah.
Assignment.
Sure.
I forget when you talk about the content. What does that mean?
Sorry, the content.
Yeah, C is equals to C is mean content, right?
Right.
Now, what is content really mean?
So it's like so let's suppose we're dealing with a situation of people have to share needles, like that can. It's basically some process of interaction between people that leads to risk of transmission. For some disease, it might be sharing needles.
Okay.
Some diseases, it might be sexual contact between two people. Some people, it might be like I sneezed near you, or cough near you in a way that could infect you.
So when you say 10, which is 10 people share the needle, or 10 people having sex?
Per day. Like each person has that much contact per day. So think of it as like they're within. The